Welcome to a new data science project. In this project, we'll be detecting brain tumors using convolutional neural networks. So let us look at the learning outcomes of this project. We will learn and understand about image classification using features. We'll learn how to clean and process images for such tasks. We'll learn about convolutional neural networks. And finally, we'll deploy our model as a Flask web app. So let us see what is image classification. From birth, we have learned to visually identify things around us. We take notice of features in something we are looking at to compare and identify. Let us take a look at a simple example. There are two images shown here, and it is obvious to us that the image on the left-hand side is an image of a car, and the image on the right-hand side is an image of a plane. Well, we clearly understand the difference between these two images. It is obvious, right? But how do we go about understanding which is a car and which is a plane? Firstly, the plane has wings, the car doesn't. The car has 4 big wheels, the plane has multiple smaller wheels which are sometimes not even visible. Although they share the features of having windows and doors, the shape and structure are completely different. These obvious features are helping us identify one from another. Now let us take a look at these images shown here. If we are asked which one shows a disease, other than to a trained doctor, it is not that obvious, is it? Thus, machine-aided image classification has seen a rise for some time now. When trained on a lot of data, it can help classifying pictures as and when needed. Be it healthcare, industry tools, etc., it has helped massively. A machine also has the same way of learning, understanding features from known data and then applying its knowledge on newer data. But the features that the machine learns are very much different from the features that we learn. We shall take a deeper look into this when we look at convolutional neural networks. So before that, let us look at our dataset. The two scans of the brain that we saw are from the dataset that we will be using in this project. The dataset has 4600 unhealthy and healthy scans of the brain, and it is contained in 2 folders. Our model will have to classify each scan. The dataset can be found on Kaggle from this particular link. So firstly, we'll import a few important libraries. We are importing libraries to help us read the images and pre-process it and plot it. We are importing Keras and TensorFlow to create the model, and these two specific classes and functions are being imported. So the load image function basically helps us in reading the image, and the image data generator is a class which will have functions which can automatically read all the data there is in the directory. After running this, we'll set our base directory using this line. This is where our dataset is. We'll set the batch size, the image size, and the input shape that we desire to use. The input shape is 150 x 150 x 1. This one denoting that the images will be changed from RGB to grayscale. Next, we create an instance of the image data generator class with parameters rescale and validation split. Rescale is basically normalizing all the images from a range of 0 to 255 pixel values to a range of 0 to 1 pixel values. Validation split is telling the object that whatever data that we find in the directory, it will be split 80% to training and 20% into validation. Next, we store the images in variables using the function flow from directory from the class object datagen. Flow from directory basically takes the directory of the dataset and automatically gathers all the images in all classes and stores it in a dictionary. So we are passing the image directory here, and we are asking it to resize the image with this parameter. It will automatically resize all the images after reading it to a size of 150 x 150. The batch size is being set to 64. Color mode will be grayscale, so that means the RGB colors will be changed to grayscale. Class mode is binary since we are dealing with only two classes, and subset is training so that it knows that we are getting 80% of the data into the training set. We can see that it has found 3,681 images belonging to two classes. Again, similarly, we'll be creating a validation dataset using the same directory and the same hyperparameters of target size, batch size, and color mode. We are setting the class mode to binary and subset to validation this time. We can see that it has found 919 images belonging to two classes. So we're going to store the class indices in labels and then use that to get the key values from the dictionary. These will basically give us the classes that it found. We can see that at index 0, the class is brain tumor, and that index 1, the class is healthy. Let us take a look at convolutional neural networks. So convolutional neural networks are very similar to ordinary neural networks. They are made up of neurons. They have learnable weights and biases. Each neuron receives some input, performs a dot product, and optionally follows it with a nonlinearity. CNNs make the forward function more efficient to implement and vastly reduce the number of parameters in the network. Using convolutional neural networks, we can reduce the number of weights that we need and the number of neurons that we need to learn the features of the image. In this image shown here, the right-hand side shows a regular 3-layer neural network with 3 inputs, 2 hidden layers, and 1 output. On the right-hand side, we can see a convolutional neural network, and we can see how it arranges its neurons in 3 dimensions: width, height, and depth, as visualized in one of the layers. The convolutional neural network transforms the 3D input volume, that being the image in this case, to a 3D output volume of neuron activations. Let us look at a few layers that make up the CNN. Firstly is the input layer. It will hold the raw pixel values of the image, having the shape, width, height, and depth. Depth is denoting whether the image is RGB, which it will have the value of 3, or grayscale, which then it will have the value of 1. The CONV layer, or the convolutional layer, will compute the output of the neurons that are connected to local regions in the input. This layer basically uses a number of filters with a kernel size to convolve with local areas of the image of the same kernel size and then learn features from there. The ReLU layer is an activation function that will apply an element-wise activation such as the max 0,x thresholding. Basically what this does is any negative value will be thresholded to 0 and the positive values will remain the same. Pooling layer will perform a downsampling operation along the spatial dimensions of width and height. So if an image is being fed with the size 200 cross 200 and it is fed into a pooling layer, it will be downsampled to a size of 100 cross 100 if the pooling layer size is 2. Finally, it will have a fully connected layer which will compute the class scores as in a regular neural network. As with ordinary neural networks, each neuron in this layer will be connected to all the numbers in the previous volume. Here we can see how the convolutional layer is working with a filter and a kernel size of 3 cross 3. The kernel is going through each pixel of the image and doing a convolutional function and creating a new learned feature based on the filter. Here we can see how the pooling layer works. So the pooling layer is dealing with downsampling the volume spatially independently in each depth slice of the input volume. So the left hand side we can see that the volume is of size 224 cross 224 cross 64, and when we perform pooling downsampling we can see that the volume has been reduced to 112 cross 112 cross 64. This is only possible if the pooling size filter size is set to 2 and the stride is set to 2. The right hand side image shows one slice from that volume. We can see that the slice shape is 4 cross 4, and with a 2 cross 2 pooling filter or max pooling filter, which takes the maximum value of the pixels in that area, we can see that the size has been reduced to 2 cross 2. So how will we be implementing our CNN model and saving the model for our web app? We'll be implementing our CNN model using TensorFlow and the high-level API Keras. we can access the layers mentioned earlier from TensorFlow and set the hyperparameters ourselves. For our specific project, we'll be adding 2 convolutional layers along with 2 max pooling layers. And finally, we'll have a dense or fully connected layer with 512 neurons. We'll also have an input layer defining the size of the image being fed into the network, and an output layer having 1 neuron since it is a binary classification problem. Lastly, we'll save our model and make a Flask app for this project. Now that we have pre-processed the image and stored it in our training and validation set, we'll be making the model. So here you can see we are importing the sequential class, and we are creating a model with that instance. We are using sequential since our model will be a linear model. Next, we are importing the layers, namely dense, convolution layer, max pooling layer, flatten, and dropout. We won't be needing batch normalization here, but it is a good practice to import all of them. After creating an instance of the sequential model, we'll be adding the layers using model.add function. So firstly, we add an input layer with the input shape 150 x 150 x 1, matching our images here. Then we add a convolutional layer with 16 filters, each of size 3 x 3. And instead of adding an activation layer, we can simply specify the activation here, which is ReLU. After that, we add a max pooling layer of size 2 x 2. Then we again add a convolution layer, this time having 32 filters, each of size 3 x 3, and an activation of ReLU. And then we add a max pooling layer of size 2 x 2. Finally, so we use the flatten layer to flatten the 3D volume into a 1D dimension so that it can be input to our fully connected neural network for training. After flatten, we are adding 512 neurons in a dense layer with the activation as ReLU. Then we are adding a dropout layer with the value 0.2, meaning that the 20% of the worst performing or the worst contributing neurons will be dropped. Finally, we have an output layer with 1 neuron with the activation as sigmoid. After creating the model, we are going to compile the model with the optimizer Adam, loss being binary cross entropy since we are dealing with 2 classes, and metrics being accuracy. Let us take a look at the summary of the model. We can see that there are approximately 21 million trainable parameters. With that, once we have created our model, we can use model.fit to fit the model on our training data. We are passing valgen as validation data. The steps per epoch and validation steps is open to experimentation. Since this is a hyperparameter, we can tune it accordingly to get the best results in loss and efficiency of the model. Here, I have already pre-trained this model for a larger number of epochs. Since it takes a lot of time to train this model, I'm not showing it here. I have added another 5 epochs here to show the final 5 training epochs. We can see the loss has been decreasing constantly, and the validation loss has been also constantly decreasing with a little bit of jaggedness, and we have a good accuracy, training accuracy and validation accuracy. Let us plot the last 5 epochs using this block here. We can see that there has been a steady decrease in the loss and a steady increase in the training accuracy. Finally, we can save our model using model.save. Next, we do some testing with our model to see if it is actually predicting the values correctly or not. We'll be using the pillow library to read the images. Firstly, we'll be creating an empty array of the shape 1 into 150 into 150 into 1. Then we'll be opening the image using the directory. Here we can see that we are opening a healthy image or a scan which shows no brain tumor. We are defining the size here, and then we are pre-processing the image and transforming it into grayscale using this function. And then we are resizing the image to our desired size here using this function. Finally, we read the image as a NumPy array and reshape the NumPy array so that we can input it in our model. Then we use model.predict to get our prediction, and we can see that the prediction is 1. Now, what does this mean? If we go to the top and see our classes, so we can see that index 1, it means that the class is healthy. So we can see, since our input image was from the healthy folder, we can see that it has predicted the class correctly. So now that we have created a model and saved it, let us look at how we go about creating the Flask web app. So let me open this directory. I have made this directory called app, and when we create a Flask web app, it needs to have a specific structure so that it can run without any issues. So firstly, we have the static folder. This folder includes all the images that we will be needing. This folder includes all the images that is being input from the HTML file and that we'll be needing for our project. All the files that are input from the HTML file will be saved here in this folder. This folder can also contain the CSS files, but we are not using that right now. The templates folder has the main index.html file. So let us open that. We can see that it's a very small index.html file. So the main parts being this form and the image and a Jinja expression that we'll look at later. Next, we have app.py, which is a script. Let us open that. And model.py, which is another script. Finally, we also have model.h5, the model that we trained and saved in the base directory. So let us look at app.py since it deals with actually creating the Flask app. So we are going to import the class Flask, and we are going to import a function render template, and we are going to import a variable request. The Flask class will be used to create an instance of the Flask app. The render template function is used to render the HTML file as and when required, and the request variable is used to get any kind of files or values that is being inputted in the form in the index.html file. Another important import is importing all the functions that we have defined in our model.py script. The model.py script is basically dealing with actually testing the image that we have input, and we are importing these functions in our app.py so that we can call them from here. So let us create an instance of the Flask app using this line and set a base directory for uploading our images as so. We are setting the allowed extensions to be PNG, JPG, and JPEG. Finally, we are configuring the app to default this directory as the upload folder. So this code block here deals with rendering the HTML file the first time we load it on our web browser. This is configuring the URL to load this index.html file. Next, this block is the main block that we are concerned with, and this will show us the output. So we are configuring the URL with the functions method. This function allows us to get any kind of file that's been submitted in the index.html to our app.py script. Then we define a function upload file, and we check whether a file has been uploaded through the form here in HTML file or not. So if request.method is equal to post, that means that in the form here, we are using the method post to send the data here to our app.py script. If the file does exist, and here you have to make sure that this name here is the same as the variable name of the file that we are inputting in our index.html. If that does exist, then it will continue. Otherwise, it will throw an error that there is no file in form. Once we press the submit button and the file does exist, it will read that file and store it in file1 variable. And next, we'll be creating a path directory with the upload folder and the output.jpg added to it. We'll save the file that is read to that path. Next, we pass that path to the image pre function in our model.py. So let us see what it does. Here in our model.py, we are importing some important libraries that will be required to read the model and make some predictions. We are also setting the base directory where our model is and loading the model using keras.models.load model. Next, we'll see the image pre function, which takes in the parameter path. So this is similar to the testing that we did in our Jupyter notebook. It is creating an empty array of size 1 cross 150 cross 150 cross 1. It is defining the size and reading the image using the pillow library. it is opening that path and reading the image and changing the image to grayscale and resizing it to our desired size. Finally, we read the image as a NumPy array and reshape it so that we can input it to our model for prediction. We return this data to app.py and it is stored here in this variable. Next, we call the function predict and send this data to that function. This function basically just uses model.predict and sends back the prediction. Finally, if the prediction is equal to 1, then we output the result no brain cancer. Otherwise, we output the result brain cancer. To render the index.html file with the result, we use render template again and send this result variable, the value being this result and this variable name being the same variable name that we have used in this Jinja expression here. Make sure that these names match so that there is no discrepancy and the app works perfectly. Finally, we run the instance of the app using this code block. So now that we know how to create the web app, let us run this and see it working in real time. So let me run this. Alright, so the web app is active on this link. Let us copy it and go to our browser. Let us paste the link. So we can ignore this image right now because this image was used as a previous testing for this web app. Let us choose a new file. We'll choose a new file from the dataset that we already we trained the model on, and let us choose an image from the healthy class. We'll randomly choose one image here, open, and submit this. So now we can see that it is correctly predicted that this image or this scan shows no brain cancer or no tumor. Let us choose another file from the other class. These are scans having brain tumor. Let us choose this image here, upload this. You can see that it has correctly predicted that this scan shows brain cancer or shows a brain tumor.